Io l'audio lo posso programmarci.
Ok. Ok.
Like the speaker will be introduced by Lorenzo, so I leave the floor, but I will give you 5 minutes before the end. Perfect.
Okay, thank you. So we are glad to have Ludovica Crosato Menegazzi from Potsdam, so Albert Einstein Institute. She's a PhD student, going to discuss her thesis by spring, and then already has a postdoc position at DESY in Zeuthen. So very young and promising researcher. Working, so she graduated in Trieste with Lara Nava, a main expert on gamma ray burst emission theory. And then she focused first on the afterglow emission, the modeling. And then now she's mostly focused on progenitors. So this kind of supernovae, peculiar stars and peculiar explosions are one of the main possible studied progenitors of gamma ray burst, and not only. So it's a very hot and interesting topic. So thank you very much, Ludovica, for coming, and have a nice talk.
Thank you. So thank you for the introduction and thank you for having me. Today I will present my main topic for my PhD research that I carried on with Shokuji Bayashi and Masaru Shibata, mainly who are my supervisors at Max Planck Institute. In these projects, I focused, as Lorenzo said, on the possibility for failed called collapse supernovae to be the progenitor of then the connection, at least with GRBs. But today I will present non-relativistic scenario, that is, so where I focus on the properties. So where I studied the variety of these wind-driven explosion in massive rotating stars. So we know, let's have a quick recap about the history and the possibility of the fate of very massive stars. We know when that massive stars, that it means basically, okay, there are several criteria, but generally above 8 solar masses, a very typical scenario is the one that they undergo to a core collapse, and then we have the typical supernova. However, it has been shown, so there are models showing that when the mass is really, really massive, so we are above 16, 20 solar masses, it is likely that during the PNS phase, the explosion fails, and then there is the direct formation of a black hole. Another ingredient is quite important, and we will discuss later about it. Okay, I lost my pointer, but is the compactness of the core, or also of the binding energy of the entire star, which is another detail I focused on. So we have the black hole, but it's not sufficient. We need also rotation. For what? To have the disk formation. In that case, what we obtain is the black hole with an accretion disk surrounding it. And if we have fast rotation, massive star, black hole plus disk, we have the perfect central engine to then not only have an outflow along basically the equatorial plane, but also likely the GRB or something relativistic ejected along the polar axis, which is likely then to be the GRBs. And also why we focus on that, because we also know that these models, these failed core collapse supernova, have been suggested to be associated with the type 1Ca supernovae, broad-lined usually. So the idea was to have also to provide in the future with this model the connection not only with the progenitor but also the supernovae GRB connection. Now we focus with these in this work on the observational properties that we can access to these. And basically one of the new and studied for the type 1C supernovae is for sure also the nickel production that we also studied. So this is, I'm working in a computational group. So what I did was writing a code and having a setup. This is basically the setup reproducing the black hole plus the disk formation. So what I have here the last picture on the right represents my grid, in which I cut out the central region where there is, and I evolve the black hole plus the disk, and I studied the hydrodynamics of the ejecta along the equatorial axis. So what I did is a 2D that can also actually become a 3D code, axisymmetric, non-relativistic, that I developed within Athena++. However, Athena wasn't supporting at that time the features that I needed for my code. So I developed my own gravity solver, solving the multiple equation to calculate the gravitational potential, that means the self-gravity of the star that I needed. I also use a free tabulated equation of state. In this case, it's oxygen-based because of the choice of the progenitor. And I decided to work on rapidly rotating progenitors. Here, for the first work, I only used Aguilera-Adena progenitors that are progenitor for these kind of stars. And then I also added totally different progenitor from Dana and Fernandez in order to have a wider spectra after having got the results. And the central gene, as I mentioned before, is cut. This is partially computational reasons, because otherwise, if I wanted to follow the hydrodynamics from the very center to the end of the star, so basically to 10 to the 10 to the 11 centimeter, it would probably, for a simulation, despite the resources that we had, the supercomputers, it would have taken years. So that was something we wanted to do. How I model and I evolve. So my initial condition is that within this 1,000 kilometer radius, I at first have the black hole. From that, I evolve the system with the forming the disk and then the outflow. So basically, there are three major terms. There is the envelope, because at first the gravity of the star is letting the envelope inflow over the disk and the black hole. So we have the fold terms and the accretion terms, which means what is accreting from the disk onto the black hole, and finally the additional term that we added, which is the wind component. So basically, as you can see, my system of equation evolving the black hole and the disk are based on a communication between the transfer of matter and angular momentum. So as I said, the fold terms are directly done through the boundary condition and computed from the falling and the gravity of the envelope, and then the accretion terms, which regulates the communication between the disk. And these are pretty important in our model. And to have a model as general as possible, we have some free, of course, parameters in my code. And one of those is the accretion timescale that regulates the accretion from the disk onto the black hole for both the angular momentum and the mass. And finally, the wind, how it is injected. Also here, there are several parameters in both the geometry that are fixed at the beginning of the simulation, but also to have simulations, so more than one, and to study the evolution of the possible wind injection terms. And here there is another free terms, which is the wind timescale. So basically, two main free parameters in my simulation are the wind timescale and the accretion timescale. Condition for the wind injection. As I mentioned before, I'm injecting the wind, but both the opening angle, the direction of the angle, and the density profile are three characteristics that are quite important to describe the wind, and they are kind of free. So they can be changed, but for all the simulation have been kept fixed, and therefore I'm injecting the wind along the equatorial plane within a 90 opening angle, so 45 and 45 above and below the equatorial plane. parabolic density profile. Why? To have the highest density along the equatorial plane, and then to have a smooth transition to the wind to the stellar density at the boundary, at the edge of the opening angle. And the other two free parameter in my simulations. So how I inject the wind is determined solving the equation of the energy for the wind, where we have the kinetic energy, the internal energy, and the gravitational potential. How is this definition made? So comparing the energy of the wind to an asymptotic value described from the asymptotic velocity as a function of the escape velocity from the disk. So here, there are other two terms, which are F thermal, describing the internal energy of the wind as a fraction of the kinetic energy, and psi. Psi is actually a Fuchs parameter we took from the literature, and that describes, that actually takes in account all the lack of knowledge about the structure of the disk. This is a quite simple model, but why we kept that so simple is to have a wider possibility, or at least a wider spectrum of scenarios that changing these parameters we can reproduce. So I did two analyses that have been published in two different papers. In the first one, what I did is fixing at the progenitor from Aguilar-Adena for a progenitor mass of a star with 20 solar masses mass, and keeping the rotational omega 0 profile. But rather, I studied the dependency of the explosion properties on other free parameters, which are the wind time scale, the accretion time scale, F thermal, and psi, as I mentioned before. In my second work that have been recently published, what I did is the other way around. So I kept the parameter of the wind fixed, but I studied the dependency on the mass progenitor and on the rotational profile of the initial star. So these are the values I varied for for the first study, and actually there are the ranges are quite broad, and this is to have as wide as possible spectra of investigation. These should go. Okay, this is a result of my simulation for the density, where you can see here the injection, how it develops and how then the outflow goes. The arrow, so the color is density, and the arrows shows the radial velocity. You can see that the wind goes along the equatorial and then expands following the hydrodynamics. The outer radius is outside the star, so we have a complete evolution, and is in time of seconds. So actually, the injection and the explosion is done within, in this case, it was, I mean, the injection happens always between 20 and 30 seconds, so it's pretty fast, because there is quite a sharp difference in the run pressure, which leads to the explosion. And then I kept following it for 1,000, 2,000 seconds, but here, of course, it achieves a convergence. Sorry, over. The first study was really interesting for us. Here I'm showing you, so with full dots, the explosion energy, and with open dots, the injected energy. This was quite interesting because the color shows, for instance, here I'm focusing on the wind time scale, and we noticed the existence of two different groups of explosion. A very subenergetic, so with an explosion energy of 10 to the 50 compared to a very highly energetic explosion with 10 to the 52. And they were quite distinct. So we were interested in knowing if this dichotomy was related either to the progenitor or to the wind. Then with the second study, we could confirm that was a dependence on the progenitor. So it's something specific of Aguilera-Adena progenitor, but still it was interesting because we could actually study and find the reason for this distinction, which relates to the binding energy of the star. In this case, we are for the 20 solar masses, but also that drives to a different explosion mechanism. So for the very explosion energy, and that relates to the round pressure. So the round pressure is so much stronger than the pressure of the infalling matter, that it can push and drive the explosion from the inner boundary to the outer boundary itself. So it's always the injected matters that covers and pushes to the outer boundary where I measure actually the explosion energy, the matter. Instead, what happens here is that we actually didn't even expect to have an explosion, successful explosion in the second case, but still we had. And the reason is that the round pressure and the pressure of the infalling matter are quite similar, if not even smaller, the round pressure. So it cannot really push and represent the matter that goes through the inner boundary to the outer boundary, covering and going across the whole star. But it works as a wall. So the pressure is still sufficient to have the matter bouncing on this front and creating then a shock front backwards that propagates to the outer boundary, where I measure it. But of course, because of the force and the energy that have been spent bouncing, it's way lower. Here, instead, there is a comparison with some observational data for basically broad lines. Some of those are also stripped envelope type 1b supernovae from Tadia and Gomez, and we can see that the reproduction goes. I mean, we are within the range, so it's fine. We could say that it's likely for space supernovae to be the progenitor of those, but we can see quite a tight correlation between the explosion energy on the y-axis and the ejecta mass that is not appearing in the observational data. So this was also something we wanted to explain, and we still found related to the progenitor. And here also we measure then the nickel mass. The nickel mass was measured with tracer particles for those that we could actually, they were always within the numerical, the computational grid. So we could actually compute the proper nucleosynthesis we used 200 isotopes. And instead for the injected, but the problem is that to compute the nucleosynthesis, we have to trace back the particles. That means all the particles that either were injected directly from the central engine, so they were at the beginning or for a certain time at a certain point outside the computational domain, we cannot be sure that about their thermodynamical history. So we assumed, and this is the difference where I write stellar and injected, we assume that they all become nickel. So it's kind of upper limit that we put compared to the lower limit, if considering that only the matter that has been always inside our computational domain produced nickel. And also here, the range actually covers the nickel mass computed by Tadia and Gomez. So also this was quite a good agreement. And then the second work, I will go quicker here. However, what we use is a reference mode from the highly energetic explosions to fix the wind parameters. And then we decided to play with the brass progenitor and the angular and the rotational profile. So the progenitor was actually studied from 9 to 45 solar masses, 40 at the end. And the rotational profile is computed as a fraction of the original one, going from half of it to 1.2. So also here we wanted to see how the rotation was affecting results. This is, okay, a very cool plot, but showing both as before the injected energy, the explosion energy, I don't have the pointer, but I mean the field, and aligned ones with different shapes are representing these actual study. The gray axes are the results from my previous study. And here, and the end, what's more, I added in the second stage of my study still 2 simulations with 16 E and 35 OC that are progenitor from not more from Aguilera-Andena, but from Dan and Fernandez, that distinguish from the other for a higher initial rotational profile. So they have higher angular momentum from the beginning. And we can see that we missed for those progenitor the connection and the strict correlation between the energy and the mass. So we could actually state and confirm our hypothesis that such a strong correlation has something to do, which is still not still unknown. I mean, we are not sure what actually is, but relates to the progenitor of Aguilera-Andena. And here, eventually, what I also did was with my remit study, we could actually provide a tool, which we found interesting, because if you want to have a tool to decide which progenitor to use, if you already know the minimum, for instance, explosion energy you need to achieve, we found a way using, for instance, our results, and that is comparing the explosion energy with the binding energy of the outer layers. So the energy of the outer layers can be computed just from the progenitor properties, so before simulation. And here we can provide a tool with our results to decide which progenitor to pick according to the explosion energy that we have measured already. So you don't have to, that you maybe need. And here there is also the same comparison with the observational data from Teddy and Gomez. And the interesting thing is, again, still seeing the strong correlation for progenitor of Aguilera-Andena, but once we move to the left and right arrow in purple that are done with Dan and Fernandez progenitors, we can see that finally we could actually reach higher ejecta mass, moving out from the alignment that we measure for Aguilera-Andena progenitors. And here the nickel is basically still more or less as before, so we have a good agreement. So here what we added is also the nickel measured by my colleague Fujibayashi with a similar, with a general relativistic simulation, and we can see that it's always covered in our range. So basically, to conclude, the summary is that for this study, I wrote my code to compute the self-gravity, which is actually an implementation to Athena code itself, also because it works in spherical polar coordinates and with external US stable. It's parallelized as everything, almost. We found a bimodal distribution that eventually we could explain and relate to the explosion mechanism. We found several characteristics of the wind, for instance, that larger wind timescale tend to provide and to cause larger explosion energy, so more stronger explosions, and we found a good agreement with observational data. In the second, we found that basically because the wind parameter we fixed were belonging belong to a highly energetic explosion from the beginning, for all the simulation we got an energetic explosion, and this is confirms that the wind actually affects the explosion in the end. We found that finally an answer is the strong correlation depends on the progenitor, and there is something in Aguilera progenitor data. And also that more massive stars with a higher entire star compactness are actually likely to generate more explosion, larger explosion energy because of a higher mass inflow rate. So, and very often in the literature, they focus on the core compactness, but it's not enough. The mass inflow rate is controlled by the compactness of the entire star. And we also provided a tool to provide you the progenitor according to the explosion energy you may need for your simulation. So thank you for the attention. And if there are any questions.
Yes, if there are any questions from the audience, and then I will check online. Francesco.
So in the light of your results, I'm going to ask you the following question. In simulations of galaxy formation or star cluster simulations that model the stellar feedback, in general, people assume that each supernova ejects the typical energy of supernova, core supernova, is 10 to the 51 erg.
Yeah.
And this is assumed for all massive stars in the whole range. So in the light of the result of your results and of your group, the ones of your group, is it still safe to assume that value for the typical explosion energy and for the entire continuous mass range?
Sure. I would say 10 to the 51 is a good assumption. However, we found that actually the explosion energy can be we are now specifically studying the phase core collapse. So the explosion is actually from a phase, the supernovae, right? It is, but it can go according to the mechanism that we found is possible to have either both explosions with a lower energy, but also reaching the typical energy of 10 to the 52 that should be the hypernovae energy. So we could cover, yes, the whole spectra. 10 to the 51 might be a good average, but still it's possible to have both higher and lower energy. Okay. In my model, yeah.
And concerning the fraction of the mass spectrum that is in another problem is the fraction of the mass spectrum of the progenitor that is interested by the explosion, because there are models by the so-called that you quoted that predict like islands of explosions in the progenitor mass range.
Yes.
So that's another problem.
This is another problem. Yeah, we didn't focus on. So probably I wouldn't have. We have the ejecta mass, right? That is the mass of the ejecta that we measure at the outer boundary. But for those, you may have a question that I was also asked from the referee, for instance, last time, was why we decided for the opening angle, because the opening angle that we put at the beginning also affects probably, I mean, for sure, the ejecta, the fraction of the ejecta mass we obtain. And this is explained in my paper and is based on the results of simulation from Fujibayashi, from them, from others also, which are always, they module the very central engine, and they see the outflow, the initial outflow, and the opening angle in their simulation is more or less the same. And also because we are non-relativistic, the effects of changing the angle doesn't affect that much in the mass outflow and the explosion ejecta, but however, this might be something related to the fraction of the progenitor mass, of course, that becoming ejecta. So it's still a question, and there are several models for that. So when you do simulation, you have to trust something, right? We decided for those, but it could be changed. In fact, it's also like the opening angle, like also the density profile would affect it. There are more. In my code, there is the possibility to change them, but you have to run a lot of simulations. So yes, there are still several models, several opinions. No, I'm still unclear what the final answer is. But for sure, this might be a good code to use to test how likely or what happens if something changes.
Other questions?
Yes, I was just wondering why for the second paper you
Yeah.
chose to fix the parameters from a high energy explosion, not from both.
And on from both, because from both it would be nice, but it was computed. That was also to consider computational costs, because I'm using a 40, supercomputer, but still for one simulation it took a couple of weeks minimum. And we decided to pick those because we were interested in highly energetic to focus on, because we knew that, as Francesco said, the typical energy is above, for the type 1c supernovae, above 10 to the 51. So we wanted to stay to be sure in that range that is the typical energy of supernovae then related to GRBs, because the next step that I will then probably do during my postdoc will be to inject also the relativistic ejecta. And the connection between GRBs and supernovae is likely to be have it with highly energetic explosions. So the low energetic are unlikely to also have the relativistic jet successfully going outside the envelope.
My question was just about this last statement you were so remarking. So if you can already get some clues from the region of what your work with the properties of gamma ray bursts. As you mentioned before, these kind of explosions are thought to be a main progenitor of gamma ray burst. So yes, when I saw this bimodal distribution of energy, so there has always been evidence of the existence of a subclass of gamma ray burst, subenergetic, very low luminosity, peculiar properties.
Yeah.
So first question was if you can connect this evidence with your finding in the first work. And this is also, for instance, for the metallicity. So there is also evidence that gamma ray burst can explode in low metallicity environments. And finally, up to which ratio. So we detect long gamma ray burst at ratios 9, 10. When we expect the stars are very low metallicity, part of them could be pop-3 stars. So if you can assume, or up to most of the time, you can assume that this mechanism could work for these very remote stars. So if you have a metallicity threshold, so low but not too low.
So I would say, starting from the first question, so for sure the two quantities we wanted to use are the two main observables that are, and they can relate to the connection, especially GRB supernovae, that are of course the explosion energy and the nickel mass. I would say that for the low luminosity GRBs, then the scenario we should investigate more is the one that he mentioned before, that is taking them and see for different progenitors, but setting some parameter for which we got a low energy explosion, a subenergetic explosion. That I didn't, but it can be still, of course, doable. In that case, we could have, if for those, with those parameters, we got still good explosion, changing the progenitor, that could be, we could do some assumptions on those as well. For now, we focus on the typical, I would say that the highly energetics are likely to be related to the typical long GRBs. And the explosion energy and the nickel mass we measured are in agreement with those of the supernovae that have been related. So we have to for now with the because the wind outflow would be those generating then the supernovae, while the ejecta, the polar axis ejecta might be the GRBs, but for sure they are in good agreement with those of the supernovae that have been actually observed and related to GRBs. So on that wide sense, for now, we can already say, yes, it's possible. For the nickel, also, I would say, so I didn't focus on the redshift is not a parameter for us now, because we are just simulating the progenitor. It would become, once injecting, of course, the relativistic GRBs, but I think there are no so strong constraints actually, because we are free to choose both the EOS equation. So we can adapt. I mean, if we are in a low metallicity environment, because those are where oxygen based, but changing the EOS, it would work. I mean, we could still use my code to model also whatever technically kind of a progenitor. Changing that, and then also maybe the isotopes working in the nucleosynthesis for the nucleosynthesis and or in the process. I mean, I remember that at first, when we consider which code to use for the nucleosynthesis, we found some that were using 21 isotopes, so very low. We already used 200, so we should be able to reproduce pretty well the whatever environment, I would say, playing with those two. So I don't think that GRB's redshift would be such a strong condition, because the code is quite flexible. Yeah.
So
I mean, yes, to describe, like, for instance, the environment or something like that. But it should be, yeah, I mean, it would become a variable for the jet, but then for the emission. Exactly. Exactly. And having the nucleosynthesis with so many isotopes and the equation of state be tabulated, it's doable.
Okay.
No, just a final comment, just when you were answering. So actually, it is true that there is a subclass of low luminosity gamma ray burst. However, some or many of them have an associated supernova. And actually, we have to say that the supernova associated to low luminosity gamma ray burst don't show properties different, significantly different from the supernova associated to normal luminosity gamma ray burst. So this may be an evidence that actually the connection between the luminosity gamma ray burst and the properties of the progenitor and the supernova are not so tightly linked.
Exactly. That was one of, I mean, at the beginning, the title of my thesis wanted to be unified and non-unified GRB supernovae, because there are several scenarios, but then a lot of exceptions, especially with the last observations, and also now the hypernovae and GRBs. So there are a lot of variables in the game, but I think that injecting the relativistics jet here might be a good starting point to have at least more information or to see what is expected to happen. But also another thing is that would affect the results is the wind model. The scenario is viscosity driven, neutrino driven. These would change the jet.
Okay, so let's thank the speaker again.
Yeah, I brought some chocolates from Germany.
So very important.
So if
Stay
you want,
here.
yeah, because thank you.